and lecture number 2. Today we are going to see the article change in internal energy of a system. Change in internal energy of a system. See here, suppose you consider gas is enclosed in a cylinder. Suppose this is the cylinder. In this cylinder, gas is enclosed. Suppose this is the piston. We consider this is the piston. Here gas is enclosed in this cylinder. Now we consider two stages. Same piston, same cylinder, same gas, same piston. Suppose this is the gas. Suppose this is the initial state, and this is the final state. Again we consider second case here. Suppose same cylinder is here, having same area of cross section, all that things are same. Suppose this is the piston. This is the piston. Suppose this is the gas. And we consider another one, same thing here. Same cylinder, having same all that things, same area of cross section. We consider here piston, position of piston changed. Same gas. Here this is the initial state in this case, and this is the final state. Now suppose here we consider, suppose this is figure A and all these two, these are figure B. Then initially here we consider gas is at 100 degrees centigrade, T equal to 100 degrees centigrade. Now we heat this gas by using a burner. Then here heat is supplied to the cylinder. Suppose Q amount of heat is supplied to the cylinder, and final temperature T is equal to 200 degrees centigrade. Now in this case we consider this piston is not movable, fixed piston, but this piston is movable. Here we can, this is the initial, this is the final state. Here T equal to 100 degrees centigrade. Here T equal to 200 degrees centigrade. What we have done, that we push this piston in inward direction. That means work is done on the gas, and due to that work done, this temperature rises. Here there is a compression, temperature rises to 200 degrees centigrade. Now here you see, here heat flows from environment to system, and there is change in internal energy. That means internal energy is increased. Here heat does not flow, but work is done on the system, and therefore this internal energy or temperature is increased. That means from these two experiments we consider that is very important principle of thermodynamics. That is, work is done on the system or by the system, then there is change in internal energy, or whenever heat is supplied from outside to the system, then there is change in internal energy. This is all about change in internal energy of the system. Now we will consider next article. First law of thermodynamics. First law of thermodynamics. Or we consider here work and heat are related. Work and heat are related. Suppose you can do the same thing here. Suppose this is the cylinder, and in this cylinder we can do the same here also. Here suppose this is the piston. This is the piston. Here piston moves in outward direction. Piston moves out. And we consider here, suppose this piston, this is the piston, and piston moves in. I will write here. Piston moves in. Now, suppose this is the gas molecule. Here we can say, suppose this is the gas molecule. Now, suppose this is figure A, and we can say this is figure B. Then in this case, what happens? That is, during expansion, there is an expansion of gas molecule. That means gas molecule strikes the piston and lose their momentum and exert pressure on the piston, and piston moves outward. That means gas does positive work. See here, positive work. Gas does positive work. Now here in case B, during compression, that is gas molecule striking to the piston gains momentum. Here gas molecule striking to the piston gains momentum. Here molecule lose momentum. Here molecule gains the momentum, and gas does negative work on the piston. Here gas does positive work on the piston, and here gas does negative work on the piston. This is all about. That means when there is an expansion, that means gas molecule strikes to the piston, loses momentum, there is expansion, and here gas does positive work on the piston. And what is in this case? Here piston strikes the molecule, therefore gas molecule gains the momentum from the piston, there is a compression, and there is negative work on the piston. That means gas molecule does negative work on the piston. Now we consider here, suppose this is the cylinder. Suppose this is the cylinder, and in this cylinder, suppose this is the piston which is movable. This is the movable piston. This is the movable piston. Now, suppose we consider here, this is the system. We consider this is the system, gas enclosed in the cylinder. A be the area of cross section of this piston. Now, suppose piston comes here. That means there is expansion. Piston comes here. Through distance, that means piston displaces through distance dx. Suppose F is the force exerted by gas on the piston, then this F is given like this. F is equal to P into A, where P is pressure, A is the area of cross section. That means F is equal to, we write here, suppose F is equal to P into A. Now, if piston moves through small distance dx, then work done, we write here dW be the small work done. dW is equal to F into dx, which is equal to, suppose this, we write here value of this F equal to PA. From this here, then we can write here PA into dx, or I can write here P into dV. Suppose this is equation number 1. Now, if volume changes from initial volume VI to final volume VF, then W is equal to total work done. We can write here integration VI to VF P dV is equal to P VF minus VI. Suppose this is equation number 2. When Q is heat added to the system and system does not do any work, see here we consider two cases. Q is heat added and system does not do work, W is equal to 0. Then change in internal energy delta is equal to, we can write here Q. This is first case. Q be the amount of heat added, W is equal to 0, then delta is equal to Q. Now we consider second case. Suppose system does work and no heat is added. System does work and no heat is added. Then internal energy decrease. That means W is positive, delta U is negative. And we write here delta U is equal to minus W. Here Q is equal to 0 and delta is equal to minus W. And therefore we can write here delta U is equal to, if we combine these two, then delta is equal to Q minus W. Suppose this is equation number 3. Or Q is equal to, we can write here delta U plus W. Suppose this equation number 4. The quantities W and Q can be positive, negative or 0. Therefore delta U is also positive, negative or 0. Now we consider here suppose 3 cases. Suppose this is the system. And suppose we consider U equal to, we can write here, delta U is equal to 200 joules. This is the energy given from surrounding to the system, and we consider here H, heat lost by the system. H is the heat lost. H is equal to, we can write here, suppose 100 joules. Then we can write here delta. Suppose here we write Q be the heat given. And H be the that is heat outside. Then we can write here delta U, we write here that is Q equal to 200 joules and W is equal to work done. W is equal to 100 joules. Then we can write here delta U is equal to Q minus W, means we can write here 200 minus 100, that means 100 joule. This is the change in internal energy. Increase in internal energy, we write here suppose increase. Now we consider second case. Suppose this is the system and suppose it is taken from the system. That means Q equal to, we write here 200 joules and H is equal to minus 100 joules. Then we can write here delta U is equal to 200 minus 200 taken out. Minus 200 minus 100 means we get here minus 100 joules, and here we consider delta U is less than 0. Internal energy decrease. Here we write delta U is greater than 0. And we consider suppose third case. Suppose this is the system and Q equal to minus 200 joules and H is equal to, W is equal to again 200 joules. Then we can write here that is delta U is equal to 200 joules taken. We can write here delta is equal to Q minus W, that means which is equal to, here also minus 200, that means is equal to minus 200 minus 200 means is equal to 0, and delta U is equal to 0. No change in internal energy. This is all. And now here you see the first law of thermodynamics is extension of law of conservation of energy. Here you see heat or work, both are energies. Then here we consider that this is the extension of law of conservation of energy. This is all about first law of thermodynamics. Now we will consider next article, thermodynamic state variables. Thermodynamic state variables. Here first we will consider property of a system. Property of a system or a system variable. Property of a system or a system variable. See here, it is any measurable or observable characteristic of a system when the system is in equilibrium. And property is also called as state variable of the system. We consider here, suppose pressure, volume, temperature. We write suppose capital T. Temperature, pressure, volume, temperature, capital T. Now density, rho, mass, m are some variables that are used to describe the system. Now in this we consider two types of variables, intensive and extensive. Intensive and extensive variables. What is meant by intensive and what is meant by extensive variables? Intensive variables, this here. Intensive variables does not depend on size of system. And extensive variables depends on size of system. This is the main difference. This does not depend on size of the system. This depends on size of the system. Now suppose system is divided into two equal compartments. Then we consider here pressure P, temperature T, and density rho are same in both compartments. These are same in both compartments, and these are intensive variables. And the total mass M, internal energy U of the system are equally divided into two compartments, and these are called as extensive variables. This is all about thermodynamic state variables. Now we consider next article, thermodynamic equilibrium. Thermodynamic equilibrium. Now when the system is in mechanical, chemical and thermal equilibrium together, then it is said to be into thermodynamic equilibrium. See here, one by one, 1, 2 and 3. Suppose first we consider mechanical equilibrium. What is meant by mechanical equilibrium? When there are no unbalanced forces, between various parts of the system and surrounding, then that system is said to be into mechanical equilibrium. Now we consider here next, what is meant by chemical equilibrium? When there is no chemical reaction, between various parts of the system and surrounding, then it is called as, that system is said to be into chemical equilibrium. That means chemical composition is constant. I will write here, chemical composition is constant. Now here we can see the third one, thermal equilibrium. When temperature of the system is constant, T is equal to constant, temperature of the system is constant or doesn't change, then it is said to be into thermal equilibrium. And when the system is together in these three equilibriums, mechanical, chemical and thermal equilibrium, then that system is said to be into thermodynamic equilibrium. Now we consider next, thermodynamic state. Thermodynamic state variables and equation of state. Thermodynamic state variables and equation of state. Here you see, thermodynamic state variables, pressure, volume and temperatures and mass M. It changes, then that system is not in equilibrium. And when these two all are constant, then it is in the equilibrium state. The various states are not always independent. They can be mathematically related. Then the relation between these three is called as, that is the equation of state. For example, I will write here PV is equal to nRT. This is the ideal gas equation, and this we call it as the equation of state, where P is pressure, V is volume, T is temperature, N is number of moles, and R is constant. And if we represent graphically, suppose this is the graphical representation. Here we take pressure, here we take volume, and suppose here this is the state A, it comes to state B. Suppose this is the state B. Suppose here we write V2 P2, and here we write final and initial V1 P1. Suppose V1 P1, here we write V2 P2. That means here we consider this is the P1 pressure, this is the P2 pressure, this is the V2 volume, and this is the V1 volume. And here you get, that is volume increases, pressure decreases. And if we consider B2A, volume decreases, pressure increases. That means here from A to B, here there is a expansion, and from B to A there is a compression. That means whenever pressure decreases from P1 to P2, then volume increases from V1 to V2. Or if we consider if pressure increases from P2 to P1, then volume increases from V2 to V1, and this all change takes place at constant temperature. And so this curve is also called as isothermal curve. Okay, I hope you all understand this. In next article we will see the PV diagram. Okay, thank you.